this is what a neural network looks like. So this is a fitted neural network to the famous iris data set, if you're familiar with it. Um, you the This model has as input the sepal length and the petal length. I didn't know what a sepal was. The petals of a flower are clear. The green parts underneath that look like petals, those are sepals. So you measure the length and the width of the sepals, and you enter that into the model in the four nodes that are under input, and the model processes that data through the parameters and the linkages between the two hidden nodes, and then it produces an output value, and you take the largest output value as the indication of the species of the iris. And one reason I show you this is I actually wanted you to see a real neural network as opposed to like a diagram. The other thing is that, this is pretty complex. If you were to use a linear discriminant function or a regression model, you'd have a much easier to understand model. It's hard to understand this model. You could probably work your way through it. Even doing that, I think, would make it hard for you to understand what the model is. This model, by the way, I count 39 parameters to estimate this model. And every neural network has an input layer, it has hidden layers, and it has an output layer. This model is not particularly big with 39 parameters. It's pretty small. And I don't have time to talk about training neural networks at great length, but a neural network doesn't learn, or the learning in machine learning really means that you fit the model just like you fit any statistical model. You train the model, and that means that you improve its parameters by doing a model fitting procedure. And the model doesn't spontaneously learn; it never spontaneously learns. At least I'm not aware. I'm sure that somebody's exploring that, but the kinds of models that we're likely to run into today do not spontaneously learn. That includes things like ChatGPT or Bard. And the algorithms for training neural networks are not like other algorithms. If you have any training in statistics, they're not statistically optimal like the calculation of regression weights. They're heuristics. And so you continue to make the model better, maybe evaluating the performance of the model after every iteration, and you stop when the performance stops improving, or you run out of funds for compute or something like that. And the large language models that we're interested in, also deep learning models, require really, really large data sets. Like the English language fails me for describing how large these data sets are. For example, GPT-2, which is obsolete by a couple iterations, used 8 million web pages as its training data set. GPT-3 used 40 terabytes of data. That's an enormous amount of data. We don't know what GPT-4 used. I'm sure it used GPT-3 plus some additional, maybe with some editing, but probably something on that order, a little bit bigger. But we do know that the training cost OpenAI over $100 million. So we're talking about really, really, really big models.